I'm here to discuss something about my project, that is thermal acoustic refrigeration. As you all are hearing, this is a project on refrigeration. So as an engineering student, whenever refrigeration comes into your mind, what all things you find? You find compressor, you find evaporator, you find the thermostatic valve. So if you are using all this, you need a refrigerant, right? When you are using a refrigerant, it means a chlorofluorocarbons, which is very harmful for this environment. As you all know, in this world, the growing rate of pollution and the harmful gases like chlorofluorocarbons are increasing in rapid rate. So what is happening? Our ozone layer is getting depleted, and due to that, the global warming is taking place. So the sole aim of our project was to find a refrigeration system which does not use any of this refrigerant, that is freon. So in our refrigeration, the thermal acoustic refrigeration, what we have shown is that the refrigeration can be achieved using sound. So what happens, the basic principle I will explain you here. What happens, the sound is allowed to pass through a tube, inside a tube, where this sound wave is of sinusoidal nature, and it is of constant frequency. The air is introduced, air or any other gases like inert gases are introduced in that very pipe. So what happens, when the sound wave propagates, the compression and rarefaction takes place for every positive and negative half cycle. So in the region of compression we have high temperature, and in the region of rarefaction we have low temperature. So we can see that the temperature difference is creating. Using this same principle, the temperature difference can be created and a product can be refrigerated. That's what is the sole purpose of our project.
In order to demonstrate the cooling by means of the sound, we have made a small conceptual model. Actually, when we inquired about making this conceptual model, all of the main departments outside this campus told that cooling by means of sound cannot be actually demonstrated practically. It cannot be actually made. So efficiency was not at all a factor of consideration when we made this conceptual model. We just wanted to make sure that actually this model works. So we made a conceptual model which actually did work, and it gave us a temperature difference of about 2.5 degrees Celsius below the room temperature and 2 degrees Celsius above the room temperature within 5 minutes, and this cooling was done within 5 minutes. So sound was actually, we have downloaded a software which could produce sound frequencies of particular desired frequencies of sound, and this using this software we produce sound, and this sound is sent through amplifier unit which amplifies this sound, and again a 40-watt speaker was used which to transmit this sound to a resonance tube. This resonance tube was nothing but a PVC pipe. We used a PVC pipe, and it was closed at one end and it was completely sealed, and this 40-watt speaker was placed in a rectangular wooden box which was also completely sealed. All the sealings was necessary because we don't want any other outside sound to come inside the resonance tube, and also the inside sound to go outside. So when the sound passes through this resonance tube, the particles inside the resonance tube get compressed and rarefied, and when compression takes place, temperature of that region rises, and when during rarefaction the temperature drops, and this was the main concept used. And actually when tube is introduced, the whole amount of particles inside the tube will not be taking part in this heat transfer. Only those particles which are closer to the tube plates will be taking part in this heat transfer. So in order to make the entire amount of particles inside this tube to take part in the heat transfer, we introduced a new concept of stack. The stack is nothing but it is a closed arrangement of several paper stacks which is arranged in the form of, which acts like several tubes inside a single tube. The distance between the main tube layers is decreased, and each individual tube layers were subjected, and the standing wave is when propagated through this stack, and it travels and comes back through the stack, and then temperature of the particles inside these stacks also get increased, and every particle within this tube gets participated in the heat transfer process, and we got a temperature of 2.5 degrees Celsius at one end where the compression takes place, and where the rarefaction takes place we got a temperature rise of where the rarefaction takes place we got a temperature drop of 2.5 degrees Celsius, and temperature rise in the compression region which was about 2 degrees Celsius above the room temperature. That was our project about thermal acoustic refrigeration.